Hi, today we're going to take a look at how we can find the distance between a point and a line in 3 dimensions. So we have this line represented by this vector u, and we have this point not on the line q. Now we got to kind of imagine that this is being in 3 dimensions, and we want to find the distance between these two. Of course, the distance isn't that bad. I mean, I can identify the distance by just looking at the norm of our vector. But to get the distance of this is a little bit more tricky to do, because even though I'll know point Q, I don't necessarily know the point perpendicular of Q and U. So point Q to the line U. So to do this, we're going to get a little bit tricky here. We are going to pick a point somewhere not directly underneath Q. We'll call that point P. Now I can write this vector PQ, and that goes along vector u right here. Now, since I have vector u, I have q. If I look back to pre-calc, I can add these two vectors together using the head to tail method, and what we wind up with is a parallelogram. Now this parallelogram, it has a height equal to the magnitude of our normal vector. And the base of our parallelogram has a magnitude of u. It's u's magnitude. From geometry, we learned that the area of a parallelogram is given by the following equation. A equals base times the height. Well, if we look at our parallelogram, the base is just the magnitude of u, and the height is the magnitude of our normal vector. So that's the area of a parallelogram. Well, we also learned that the area of a parallelogram in vector form is just the magnitude of the cross product of PQ crossed with u itself. So if I take PQ, cross it by u, that gives me my area. This is one of our equations for the area of a parallelogram. So we have two competing areas of parallelograms here. But remember, the whole idea is to find the distance between the point Q and our line represented by vector u right here. Well, of course, that distance is just going to be the magnitude of n. So the distance that we're looking for is the magnitude of n. That's what we want to find. That's the distance between the point Q and the line. To solve for this, we can use algebra. Well, we know the area is equal to base times height, and the area is equal to the magnitude of our cross product. So therefore, we can also say that if I were to multiply the base times the height to get my area of my parallelogram, that's going to equal the cross product of our magnitudes. And it doesn't just a little bit of algebra here. I can solve for our distance. The length of our normal vector is going to be the magnitude of the cross products of PQ, vector PQ and u, whoops, got my hat there, divided by the magnitude of our normal vector. And this is our distance equation. Distance from a point to a line. So let's take a look at an example real quick. Let's say we have this line. X equals 2y equals z minus 1. Notice this is in parametric form. And we have this point not on the line, 0, -2, 3. And what we want to do is find the distance between them. So to do this, first things first, if I call this point Q, that's the point not on the line, I now need a point P on the line. So that's the first thing we have to do. I can do this by just letting each of these equal to t. For example, t would equal x, 2y would equal t, z minus 1 equals t. Put them in their parametric form, and I can solve this. X is equal to whatever t is, y is equal to t over 2, z is equal to t plus 1. So if I pick a t value, let t equal, let's say, 0, for instance, x would be 0, y would be 0, z would be 1. So the point on the line would be 0, 0, 1. And there's point P. So this point would be on the line. In other words, graphically, we would have something kind of like this. There's my line. Q, which is up here, which is at 0, -2, 3. And then we have point P anywhere on the line, 0, 0, 1. So what we need to find now, according to our rule up here, PQ. So PQ can be represented by the vector 0 minus 0, -2 minus 0, and 3 minus 1, which is 2. So there's PQ. Next, we need to get N, our normal vector. Well, to get the normal vector, that just comes from the coefficients. To get N, we look at we're looking for N, sorry about that. To get U, that comes from our line. This is U. So to get U, that comes from our line, and I can also get that from my parametric form right here. U is a direction vector, so x is changing by 1, y is changing by 1/2, and my z's are also changing by 1. So now we're ready to go ahead and get our distance. To get the distance, we're going to take the magnitude of their cross product, PQ cross with U, and then we're going to divide that by the magnitude of U. Whoop. Kind of weird. I should probably fix that to make that a U, right? It's my algebra there. Sorry about that. You all probably noticed that beforehand, but sorry about that. So when I find their cross products, that's easy enough to do. So let me go ahead and do the cross product over here. This is PQ cross U. To get the magnitude of the cross product, we do I, J, K, 0, -2, 2, 1, 1/2, 1. And what you wind up with is the vector -3i plus 2j plus 2k. And when you take that magnitude, you're going to get the square root of, this becomes 9 plus 4 plus 4 over the magnitude of u, which we got up here is going to be 1 plus 1/4 plus 1. And we wind up with the square root of 17 over the square root of 9 over 4, or 2/3 times the square root of 17. And that's going to be the distance between Q and U. That's the distance we found. Right there. Okay? So I did kind of mess up here. Please fix that. I do apologize for that. I hope you enjoyed this video, and I will talk to you later. Bye.